Hello everyone, myself Subhash Bhagat. The title of my talk is Min-Max Gathering of Oblivious Robots. It's a joint work with Dr. Anisur Rahaman Molla. The outline of my presentation is as follows. First introduction, then problem definition, our contribution, then underlying model of our paper, outline of the proposed algorithm, and finally future ones. A robot swarm is a collection of small, autonomous, inexpensive robots working cooperatively to accomplish tasks like moving big objects, cleaning big surface, surveillance, and others. One of the main objectives of our research is to identify minimal sets of capabilities of the robots required to solve problems like gathering, arbitrary pattern formation, flocking, circle formation, and others. Now we define the gathering problem as follows. Given a set of robots deployed in the Euclidean plane, the gathering problem requires the robot to coordinate their movement to meet at a single point which is not known to them a priori. The min-max gathering problem, in addition, requires the robot to minimize the maximum distance traversed by any robot. We first present an impossible result which states that the min-max gathering problem for oblivious robots with non-rigid movement is not solvable if robots do not have local weak multiplicity detection capability. And this result holds even if robots are fully synchronous and they have one axis agreement. Then we present a distributed algorithm for the min-max gathering problem for asynchronous robots with non-rigid movements under the assumption of local weak multiplicity detection capability and one axis agreement. The underlying model of our work is as follows. Robots are autonomous, means they work without any centralized control. They do not have any identity. All of the robots have same capability and they run the same distributed algorithm. An active robot executes a computational cycle consisting of 3 phases: look, compute, move. In look phase, it takes a snapshot of its surrounding to obtain the location of the other robots. In compute phase, it computes a destination point. In move phase, it moves towards the computed destination point. The activation of the robots are controlled by an asynchronous scheduler. Robots are oblivious, means they do not carry forward any information from their previous computational cycle. Robots do not have any explicit message passing capacity. Initially, all robots are stationary. They do not block the vision of the other robots. A robot can obtain location of all the robots in the system. Robots are represented as point in the Euclidean plane. Robots do not have any global coordinate system. However, each robot has its own local coordinate system. The center of the local coordinate system is the current position of the robot, and the direction and orientation of the local coordinate system may vary among the robots. However, in this work, we assume that robots have agreement on the direction and orientation of exactly one coordinate axis, and the direction or orientation of the other coordinate axis may vary. Robots' movements are non-rigid, means an adversary can stop a robot before reaching its destination point. However, to guarantee finite time reachability, it is assumed that there exists a delta greater than 0 such that whenever a robot moves, it moves at least minimum d and delta distance, where d is the distance of its destination point from its current location. We assume that robots are endowed with local weak multiplicity detection capability, which enables a robot to identify multiple occurrences of robots at its current location, not at the other locations, only at its current location. And a point with multiple occurrences of robots is called a multiplicity point. The min-max gathering problem for robots deployed in the Euclidean plane was first studied by Bhagat and Mukhopadhyay. They first proved an impossible result that the min-max gathering problem for oblivious robots with non-rigid movement is impossible to solve if robots do not have any agreement on the coordinate axis. And this result holds even if robots are fully synchronous and they have multiplicity detection capability. Then they came up with an algorithm for non-oblivious robots, having externally visible lights. So robots are endowed with externally visible lights, which can assume a finite number of colors from a predefined set of colors. Each color represents a state of state of the robots, and robots can remember some information from their previous computational cycle using the lights of the using their lights, and they can also communicate some information between them. So consider a set of robots deployed in the Euclidean plane. Secti 0 denotes the smallest enclosing circle of the robot position, and OT0 denotes its center. So now we state an important geometric property, which says that given an initial robot configuration RT0, the center OT0 is a unique point which minimizes the maximum distance from any point of RT0 to it. The point OT0 is known as the Euclidean one center. So the outline of our algorithm. So this property implies that in order to have a solution for the min-max gathering problem, all robots should gather at the point OT0, the center of the initial smallest enclosing circle. However, this point doesn't remain invariant under the movement of the robots. Once robot starts moving towards this point, the smallest enclosing circle changes, so does its center. So the question is how to relocate this point even if the smallest enclosing circle changes. Our algorithm has two phases. One phase is multiplicity creation phase and other is gathering phase. During the multiplicity creation phase, a unique multiplicity point is created at this point. Recall that multiplicity point is a point which contains more than one robot. So in order to do it, we first compute a subset of robots known as guards, which are sufficient to define the initial sec. So the robots which doesn't belong to this set, even if they move towards this point, the smallest enclosing circle remains invariant. We use one-axis agreement to compute this set H, and it can be proved that H contains minimum 2 robots and maximum 4 robots. Now recall that the system contains at least 6 robots and H contains at most 4 robots. So there are at least 2 robots at least 2 non-guard robots which are able to move to this point, OT0. So once at least 2 robots reach OT0, this point becomes recognizable by the robots lying at this point. So our algorithm during this multiplicity creation phase moves the robots which doesn't belong to this set. So once all the non-guard robots move toward are gathered at this point, the gathering phase starts. So during the gathering phase, once the robot starts moving towards this point, OT0, the smallest enclosing circle changes. So during this phase, we cannot recognize this point as the center of the smallest enclosing circle. So how to recognize this point? So we design the movement of the robots in such a way that OT0 either lies in the interior of the convex hull of the current robot configuration, or its y coordinate is greater than the y coordinates of the other robot positions. So there may be a situation when the system contains exactly 2 robot positions. So as we mentioned that during the whole execution of the algorithm, we create exactly one multiplicity point. So this robot can easily identify, okay, I am not lying at the multiplicity point, so I should move to the other location. By proving, after proving several lemmas, we came up with this theorem, which states that the local weak multiplicity detection capability and one-axis agreement are necessary and sufficient condition to solve the min-max gathering problem for oblivious robots. So we would like to study the min-max gathering problem in presence of obstacles. So when the deployment field contains obstacles, so the task is to gather the robots at one of the geodesic centers. And our future plan also includes to extend our study in the three-dimensional Euclidean space. Thank you.